Next up on our discussion on vector algebra is component method. Component method is used for adding vectors together. And you'll recall if you apply negative of a vector, you'll also be doing vector subtraction. So component method can also be used for vector subtraction. It's because vector subtraction is basically vector addition with the application of negative of a vector. A vector can be divided into components. And by components, we're talking about x component and y component, horizontal component, x component, and vertical component, y component. A one-dimensional vector has only one component, so it's either vertical, it only has y component, or it is horizontal, it only has x component. A two-dimensional vector has two components, whereas a three-dimensional vector has three components. Since for the most part, we'll be limiting our discussion with the x and y components, so up to two-dimensional vectors for the most part, our discussion for component method. So as mentioned, in terms of the x and y axis lines, a one-dimensional vector will either be an x component or a y component, whereas a two-dimensional vector will have both x and y component. You can use SOHCAHTOA to divide a vector into its components. SOHCAHTOA, sine is equal to opposite over hypotenuse. Cosine is equal to adjacent over hypotenuse. And tangent is equal to opposite over adjacent. That is to say, with our vector, we will draw a right triangle and then we apply SOHCAHTOA to get the components. For instance, say the position of an object, a bust, vector A, is 5 meters, 35 degrees above positive x. So 35 degrees above positive x, you have the location or position of our object, vector A. The magnitude of our vector A will be on this side of the triangle. We complete the triangle by drawing the horizontal side and the vertical side. We have a right triangle. One of the angles is 35 degrees. So if we apply SOHCAHTOA, say cosine of 35 is equal to adjacent divided by the hypotenuse. The horizontal side of the triangle is the x component, the vertical side is the y component. So the adjacent side to 35 degrees is the x component ax. So cosine 35 is equal to ax divided by hypotenuse 5 meters. 5 meters, ax will be equal to 5 meters cosine 35 degrees. If we use sine function, sine 35 is equal to opposite over hypotenuse. The opposite side is the y-axis, ay. Hypotenuse is 5 meters. So, Isolating AY is equal to 5 meters sine 35. We have our x component and y components of vector A. Note that the x component and the y component are also vector quantities. They have direction. Taking into account the direction of AX will be positive x direction, AY will be positive y direction. So both AX and AY are positive with regards to sign convention of x-axis and y-axis. Positive x direction is negative. Positive x direction is the positive direction. Negative x direction is the negative direction. Positive y direction is the positive direction. Negative y direction is negative direction. Vector AX, x component of A. Vector AY, y component of A. If you add the two components, AX plus AY, you get your vector A. Since you have positive and negative directions for our components, a component heading in the negative direction will be given a negative sign. So for instance, if now the location of the object is here, 9 meters, 15 degrees below positive x, applying again SOHCAHTOA, you draw vector A, vector B, then complete the triangle by drawing the horizontal side and the vertical side. You have a right triangle. The horizontal side is the x component, bx, and the vertical side is the y component, by. Taking into account the orientation and direction of vector B, we see that bx, x component, is positive x direction, whereas by, y component, is negative y direction. So if we now apply SOHCAHTOA to get the components, cosine 15 is adjacent over hypotenuse, bx over 9 meters. Isolating bx, you get bx is equal to 9 meters cosine 15 degrees. Positive because bx is positive x direction. If we use sine function, sine 15 degrees is opposite over hypotenuse. Opposite is by, y component. Hypotenuse is 9 meters, so you have by over 9 meters. Isolating by, you get by is equal to 9 meters sine 15 degrees. By is negative y direction, so you have negative sine. So by is equal to negative 9 meters sine of 15 degrees. X and y component of bx, by. If you know the x and y component of a vector and a vector and its x and y components form a right triangle, we can use the x and y component to determine the vector. We can use the Pythagorean theorem to get the magnitude of the vector. So if you know ax, ay, use Pythagorean theorem. A is equal to square root of ax squared plus ay squared. You have the magnitude of the vector. And then to get the angle of orientation, you use tangent function. Tangent is opposite over adjacent. If this is our angle orientation with respect to the horizontal line, the opposite is the y component, the adjacent is the x component. So tangent theta is equal to absolute value of ay divided by absolute value of ax. You have, you have the absolute value to get rid of any negative signs in the components. Then you get the inverse tangent, you get the angle theta. Component method, as mentioned, is used for adding vectors together. When using the component method, follow these steps. Each vector that you are adding in the component method, divide each vector into its x and y components. And of course, apply the positive, negative sign conventions for the directions of the components. After dividing the vectors into their components, add all the x components together, and you will get the x component of the resultant vector. Add all the y components together, you get the y component of the resultant vector. So going back to the previous slide, you know x and you know y component, ax, ay. Knowing ax, knowing ay, you'll be able to get the magnitude of a. So the same goes for our resultant vector. You know the x component of the resultant, you know the y component of the resultant. Use Pythagorean theorem to get the magnitude of the resultant vector. And then use tangent function to determine the angle and direction of the resultant vector. To illustrate these steps, consider the following example. So consider the following problem. You have a hedge maze, and it is formed by tall rows of hedges. You enter the maze, searching for the center point and then for the exit. In doing so, you undergo three displacements, D1, D2, and D3. D1 is 6 meters, 40 degrees above positive x. D2 is 8 meters, 30 degrees to the right of negative y. D3 is 5 meters, heading towards positive x direction. Determine your resultant displacement from the time you entered to the moment you exited the maze. In entering and leaving the maze, you have three displacements, D1, D2, D3. The resultant displacement is dr is equal to d1 plus d2 plus d3. Component method steps. Divide each vector into their x and y components. So in terms of this equation, you have the x component, drx is equal to d1x plus d2x plus d3x. And then you have the y component, dry is equal to d1y plus d2y plus d3y. So use your component method to determine the x component of d1. which will give you 4.596266659 meters. X component of D2, again, use your SOHCAHTOA as we have described before, which will give you D2X is equal to 8 meters sine 30 degrees or 4 meters. D3X, D3 is towards positive X, so all of the 5 meters is X component. So D3X is 5 meters. Adding all the X components together, you have DRX is equal to 13.59626666 meters. We do the same thing for the Y component. So determine D1Y, D2Y, D3Y. D1Y will give you 3.856725658 meters. D2Y will give you negative 6.9282033 meters. D2Y is negative Y direction. Going back to the previous slide, D2 is 8 meters 30 degrees to the right of negative Y. If you look at the Y component, it is in the negative Y direction. To the right of negative Y, so negative Y direction. The Y component of D2. Then D3Y is 0 because D3 is horizontal. All of it is on the x-axis. All of it is in the x component. So D3Y is 0. No Y component. Adding all the Y component together, you have DRY is equal to negative 3.0714777572 meters. So you have DRX, X component of the resultant, DRY, Y component of the resultant. If we draw DRX and DRY, DRX is positive, DRY is negative. We complete the right triangle by drawing the hypotenuse. The hypotenuse is our resultant vector, dr. Dr is hypotenuse. Magnitude of dr is hypotenuse, so we just use Pythagorean theorem. Dr is equal to square root of drx squared plus dry squared. That will give you 13.93888236 meters. The angle orientation of dr is angle theta r. Getting the tangent of theta r. Tangent of theta r is just equal to opposite dry divided by adjacent drx. Don't forget to apply absolute value to get rid of any negative signs. We know dry, we know drx. By getting the inverse tangent, we are able to get the angle theta r, 12.72977998 degrees. If we look back to our drawing of our dr, drx, and dry, you have angle theta r below positive x-axis, x-line. That will give you the direction for dr. Dr, therefore, is 13.939 meters, 12.730 degrees below positive x. You have the component method. Again, follow the steps for component method. Divide each vector into x and y components. Add all the x and y components together to get the x component of the resultant. Add all the y components together to get the y component of the resultant. Use Pythagorean theorem to determine the magnitude of the resultant vector. And use tangent function to determine the angle and direction of the resultant vector. And in doing component method, you are adding vectors together. So that's it for now. That's it for our discussion on component method. In the next video, we'll talk about unit vectors. So that's it for now. Thank you for watching.